you do not know what a function really is. And this is understandable, because in high school you mostly encounter a certain subset of functions and the general idea is easily lost. This is also, however, very unfortunate, because functions play such a central role in many fields of engineering. They express relations between real-world quantities, so we definitely need to know what these functions really are. In this lecture, you will learn this. I will also see a few ways how we can represent a particular function. So, what is a function? Well, it's a rule to assign to any value in a set D a value f of x in a set C. So it's like an engine. You have a set D over here, an input value x, then the f works and gives you an f of x which lives in some other set C. What's essential is that your function is not just a function, but the two sets over here are quite important. Let's give some names. Well, the value x, the input of your engine, the input of your function, is called the independent variable. It can be chosen independently. You can take whatever value you like. But once you specify this independent value x, then the output f of x is fixed, is given in terms of this independent variable. And since f of x is given, this f of x is called the dependent variable. It depends on x, so that's where the name comes from. On the input side you have the independent variable or variables, maybe more. Here you have the dependent variable or dependent variables, there may be more here as well. Well, the set over here of all allowed inputs is called the domain of the function f, and the set over there on the output side in which all output values live, that one is called the codomain of f. And together they constitute the function. So how can we describe a particular function? Well, we have actually 4 ways to do so, and each of them has its own merit. First of all, verbally, in words, you tell what the function does. This is actually not trivial. It's quite essential when you're starting to model a certain engineering process. Then, second, numerically, in a table. For example, if you do some measurements and you measure a relation between 2 experimental quantities, you have a table. Thirdly, algebraically, by an equation, in order basically to summarize the information of the table. And fourth, visually, by drawing a graph of the function. All information is already in the equation, but it's usually nicer to give a graph in order to be able to visualize how the function actually looks. So how's that in an example? Verbally, f of x is a function which squares any real number x. That's how you would describe a relation verbally between input and output. Then, numerically, in a table, you have x and f of x. You put the different real values x. Yeah, you cannot put all, obviously, because there are infinitely many. So we just put a few of them. X here, and the squares f of x over there. So this table contains some information of f, but just a limited number of function values. Algebraically, f goes from R, the input is all reals, you can put all reals into your function, and the output is a real number. So the domain is R, and codomain is R, because your output is a real number. And f of x equals x squared, that's an algebraic description. So you see, a function is not just this formula over here, but the function is, well, all of this. You also need the domain and the codomain. And that's what's quite usually lost when you're at high school, because often domain and codomain are always R and R there. And then finally, graphically, you can make the graph. So what do? You put the axis on the x-axis, you put the function values on the y-axis, and you can put all points in the figure over here in order to get the graph of f of x, because that tells you something more than just a formula. It tells you, for example, that the function is always positive. So that's why it's always nice to have a graph. So now you know what a function is and a few ways how you can describe functions.